Alright, hello. So I want to show you a example of where equivalent time sampling, ETS, that some scopes have, a fair amount don't, can be used though. Anyway, so this is an example of PicoScope PS6000, which has equivalent time sampling. Oops, move this over here so there you can see the scope itself. And when we're in equivalent time sampling mode, I can use on, for example, these two channels, I'm going up to 50 gigasamples per second. Remember, the analog bandwidth is still limited, so 350 megahertz analog bandwidth in this specific device. But I do have a huge sample rate, possibly. So you might ask what the use of such a high sample rate with a lower analog bandwidth is, because I can't look at, for example, a 1 gigahertz or 10 gigahertz signal, even though the sample rate's so high. One thing you'll find this really useful though is phase measurement. So over here I have an FPGA board. This is a Sakura G, and I have two clocks being output by, I'm using this FPGA right here, there's two on this board, and that's a Spartan 6 LX9 device. I don't know if you can see it maybe, there you go. Spartan 6 LX9, and so I have these two clocks, and those two clocks go to the A and B input of my PicoScope. So let me just turn this off to start with, and if I start capturing, we can see there the two clocks. So there's some slight offset between them. One clock is processed by a special block on the FPGA, and one clock isn't. One clock's processed by a DCM. So I could have just used this normally. Oops, let's just do so standard edge type trigger. As another interesting note, this is where I can also show you just for fun. The 50 ohm outputs are really handy if you're trying to terminate something, because, for example, with regular DC termination, I see sort of a signal like this. When we turn on the 50 ohm, we see a much nicer square wave like what we were expecting. Anyway, that was sort of an aside. And I'm now going to switch into equivalent time sampling mode. And the primary difference here is we now have this 20 picosecond resolution. And so I've set up some cursors here to be at, this is the one rising edge, and the blue is the trigger, and the red's the other signal. And I want to see how the phase difference between these two signals is affected with, in this example I'm going to do temperature, you can do voltage or anything else. So I'll zoom in so that we can see it a little better here. And at the same time as we're doing this, I'm going to use a freeze spray on the FPGA itself. So let's see if we can move everything so you can see this all. So I'm actually using a duster, but if you hold them upside down it works the same. And as I freeze this, what you should pay attention to is what happens to the signal. So we can see all of a sudden this phase shift here. Just turn that off. Oop. Turned off the rulers, unfortunately, there. But you could see the phase shift as the device cooled down, and then I can heat it back up, and you'll see the phase shift the other way. So there you can see a tiny bit of a phase shift one direction. I'm just heating it up with my body heat here. Use a different finger now, it's warmer. And you can see that little bit of phase difference. So the equivalent time sampling is pretty cool because you can actually do measurements like this. So even though I have this, more limited analog bandwidth, you might say, I can still use it for something. In this case, I'm using it to measure the small phase differences in two different clock paths on an FPGA. So that's just one example of what you can do with the equivalent time sampling system.